I'm on the U of T Code as exec as the course coordinator for the quantitative course in R that we offer in the Department of Ecology and Evolutionary Biology. I do a lot of programming in R as well, Bash, and then I've done a lot in Python. And so today we're going to be sort of walking through some examples of unit testing in Python, but the concept of unit testing, I think, is important to realize that it applies to all languages. So you could do unit testing in R, JavaScript, Ruby, you know, pick your favorite language of choice and you could do unit testing in that language. So the basic idea is that you should be following this sort of coding framework known as test-driven development. The idea that every unit in your code, whether it be a standalone function or some class method, has a corresponding function that tests the functionality of that function, just to make sure that you're not breaking anything, essentially. This is most important for really large code bases, especially in cases where there are like a lot of dependencies. If you have code that depends on other code and you have functions that are kind of complex and are doing a few different things, you want to make sure that all of the units of your code are working as expected and so that you're not breaking anything. So if we just walk through briefly some of the benefits of unit testing, I think the biggest benefit in my view and what got me onto unit testing early on is that it facilitates debugging. When something goes wrong, your unit tests are telling you which function it is that's breaking, because that's the test that's failing. And so you know where you need to direct your attention to fix whatever bugs might be happening. It improves the quality and confidence in your code. If all of your tests are passing, then you can be confident that the code base as a whole is working as expected. It ensures changes to the code base don't break existing code. This is useful for yourself when you're just working on a really large project, but it's also really important in collaborative work where a lot of people are working on sort of different pieces of a project. Like if you're collaborating on a project and everything is sort of hosted on GitHub, everybody's sort of pushing code to the GitHub repo. It's really important to have a set of tests that are constantly operating on this code base to make sure that, for example, the changes that one of you guys push to the code base doesn't break something that I wrote or something that was already present in the code base. So it just makes sure that everything is working as expected. It is a form of documentation, if you think about it, because not like inline documentation or doc tests or anything like that, or doc strings rather, but you could look at a function that is meant to test another function and get a sense of what it's supposed to do, because you have some expected input and you have some expected output, and you could sort of look at that and get a sense of what the function is doing. And then finally, it forces you to think about your code, right? You have to think about what the expected behavior of every unit in your code is, every function, variable. You have to think about it clearly if you're going to write test cases for the code. So that's sort of my brief intro spiel on like the benefits of unit testing. What I want to do now is actually write some code. So what we're going to do is we're going to write a class. It's going to be a very simple class. And then we're going to write a test class that tests the first class that we wrote. And so this does assume some knowledge of classes in Python. Is everybody more or less familiar with classes? It's basically just a sort of Python object that holds a bunch of related information. So a class might hold variables or functions, all of which are related in some way. When you learn about Python classes, the classic example is like a class vehicle, right? Where vehicles might have a number of wheels, they might be able to move, they might be able to do all of these things. All of the information about vehicles, for example, would be stored in one class because it's all related information. So first we're going to import some functions. So does everybody have a Jupyter notebook open or some way to write Python code? Yeah, cool. So we're just going to start by importing Numpy, which is a very effective sort of numerical operations sort of library in Python that I think a lot of people are probably familiar with. So the class we're going to write, we're just going to call it var. And like all classes, the first thing that we have to write is its constructor. And this is what has to be passed to the class when creating an instance of that class. And in Python, the constructor functions, are specified using this init method for initialize. And in this case, we'll just initialize it with 2. There should not be a colon there. Self, name, and of course, we also need to pass some data. So self, for those who aren't familiar, just means that the class is sort of acting on itself. So the first argument to all class methods is going to be the class itself because it's operating on itself.
Can I interrupt with stupid questions?
Sure.
This one. Sometimes I see classes initiated with the object parent, I think.
Yeah.
Sometimes I see nothing there.
Yeah, so I think when you initialize it with parent, that's because of inheritance. Is that true, Ahmed? Because you could have classes that depend on other classes in a sort of related way. And so you could have parent and child classes. It's known as class inheritance. And so in a case like that, if you're creating a child class, then you have to pass to it its parent so that it knows where, so that Python has sort of a record of that dependency, that those classes are linked together.
List or something. So having no parent versus an object parent, what's the difference there?
Well, in this case, do you know?
I'm not too sure. I think object's just a placeholder. It's
just a placeholder. In theory, we could write this like this.
Yeah.
We don't actually have to put anything there. It's just sort of a placeholder saying that we're going to, like, we could leave it like this, which is probably a little more transparent, but it's sort of, I often see classes just written like that with object as a placeholder, and I've sort of never questioned it, but yeah. But the parent-child thing is pretty strict in that it actually says something about the dependency chain that links classes together. Does that make sense? Yeah.
Like when we build list in it and inherit list methods.
This is basically just saying that this class is an object in Python. So self.name equals name, self.data equals data. Whoa. This should. All right.
You gotta share your screen again, Mr. Murray. Seems to have disappeared. Have you seen your mug?
Good. var class. Very similar to how we just did it in the code chunk above. Instead of just initializing an integer as the data in this class, we're actually going to just create a 5x5 NumPy array of random numbers. So this is going to be a 2-dimensional NumPy array with just random numbers between 0 and 1. So remember, this is going to be run before every question, or before every single test is run. And then in the teardown, what we really all we really want to be doing is removing any evidence that any objects were created. We don't want to like keep all of these objects in memory. We just want to get rid of them, and then we'll recreate them when we test additional functions. And so that's where the GC module comes into play. You could just run GC collect, and it basically gets rid of any objects in your environment that aren't being used by anything, that don't have any pointers going to them. Anything that's not needed, garbage collection will sort of just remove them. You could use, if you only have a few of them, you could use Python's del keyword for delete and like specifically specify which objects in the environment you want to delete. So we could delete self.var1, for example, if we wanted to. But in cases where you are maybe passing or creating a lot of different instances of different classes here, and I'll show you sort of an example of this afterwards from my own work, GC collect can be a lot more helpful because it'll sort of just go through and delete everything that's not being used. So that's it for the setup and the teardown. What we want to do now is actually write functions that are going to test the functions we wrote in our var class. And so the first one is going to be test create. I think it's, and they might have changed this, but I think it's part of the unit test module that all of your test functions have to start with the word test. That's like the cue that the unit test module uses to know that this is a function that's testing a function. So in this case, the test create function would be testing the creation of that instance of the var class.
Isn't that being done at the setup? That you're initializing the var class in the setup? Yeah, here we're initializing it, but if we want to test that it was properly created, what we need to do is confirm that this object is actually an instance of that class. Because it could be the case that you, in your environment, created some other object that was called var1. And so var1 is not actually an instance of that class. It's like this other variable that you created but had forgotten about. So we want to specifically test now that var1 is an instance of the var class. And you could do this with anything. You could confirm, for example, that a variable is a float or is an integer, is a string. You can check that it has a specific form and is of a particular type, which is often very important if your functions rely on inputs being of a particular type.
You don't need the init function for this class test case?
No, you don't. Because this class is inheriting from unit test case, the constructor function would actually be part of that. So all we have to do here is actually write the test code. We don't have to write any of the constructor objects that are associated with that because it's being inherited. So all unit tests are going to have a suite of these assert statements. Assert statements return true or false, right? They'll return true if the assertion is correct, false otherwise. And so in this case, we're asserting is instance. Similarly, there's like assert is float, assert is integer, that type of stuff. Is instance self.var1 var. So let me just scroll down a little bit here. So if you just look at this code for a second, what this is doing is confirming that var1 is instance of
class var. So if var1, this variable that we created here, is in fact an instance of the class var that we defined in the previous code chunk, this is going to return true and the test is going to pass. If it isn't, then it's going to return false and the test will just fail right there. And then you'll have to go in, figure out where the problem is, solve it, and then run the tests again. And we could toy with this later and sort of break the tests and do all that kind of stuff if we want to. And then we'll write one last function as part of this test suite, which is to test the add function. This one is a little bit less obvious. So there's going to be 3 lines of code, and I'll sort of walk through them. The first thing we're going to do is create a copy of the data that is contained in var1. The second thing we're going to do is we're going to increment var1 by 1. So this is basically going to take the data that's contained in var1 and increase it by 1. So if the data was 1, it would go to 2. In this case, because the data is a Numpy array, it's going to add 1 to every value in that Numpy array, which is sort of the way that Numpy arrays are designed to work. And then finally, as the assert statement, I'm just going to write this out and then walk through it. So looking at this function, NP all close is basically takes 2 arguments. The first is a Numpy array, and the second is some other array. And what it does is it compares all of the values with similar indices, with the same indices in both arrays, and checks that they're close to one another. And what close means is sort of to some extent defined by the user. You could set the tolerance. For example, you could say that, these values have to be within this number of decimal points. And so this is really useful. All close is really useful in cases where you have arrays that are made up of floating point numbers that have many decimal points, and they might vary by like a few digits at like the 6th decimal place or something. But it's close enough that your code isn't going to break. So you could use a function like this that basically says, they have to be close within this range, but they don't have to be identical. And so as long as they're within the range, this will return true. And we're just going to use it with the default tolerances. I don't actually know what the default tolerances are, but we'll just assume that it's good for sort of our purposes here. So what we've done is we've created a copy. We've added 1 to all of the data held by var1, and then we're just confirming that the data held by var1 is now the same as that copy if we were to add 1 to it. Does that make sense? So we're sort of testing the addition behavior of that function. And then we could run that code chunk. I forgot, yeah. Perfect. So
test created, that is instance?
Is instance, yes, thanks. Assert is instance, yeah. So it turns out, as I learned today, that we can actually run unit tests from inside Jupyter. So to do that, unit test self.main. So if you were running this in, if you want to run your unit test, this is basically all you have to do is unit test.main. Because we're in an interactive session, we actually have to pass a couple of arguments to this so that it doesn't break. The first is and then the second is exit equals false. So unit test module is primarily run as a script through the command line. And so by default, what it does is it uses the command line arguments that are passed to the script as the default conditions to run the unit test through. The first argument of the command line arguments is the script itself that's run, but we want to sort of bypass that behavior. So what we do is we just pass this empty argument, and it's telling the unit test module not to use the default command line arguments, to just basically run it in this interactive session. And then exit equals false is just going to prevent us from collapsing our kernel when we run this. Again, because it's not meant to be run in these sort of interactive sessions. And then if we run that, still got an error. So we ran 2 tests and something failed. Self.var1 plus equals 1. Is everybody else's failing, or is it just me? All right. What went wrong? This is the whole point of unit testing.
Is it by add? Is that A supposed to be capitalized? Because it's like one of those methods that act on the plus, right? Never mind.
Here?
Like in the actual object, is it capital? Because I remember it being lowercase a when the name of the method by add.
That shouldn't matter. It totally matters.
Wait, what was it?
Does anybody have any clue why that makes a difference?
It's like a special type of function.
Oh, it's because of, yeah.
Because when you say object plus 1, it's the plus is handled
Yep.
by that special method.
Yep. Totally.
Cool. I'm still getting in there though, and I did that.
Yeah. No, that was a good catch. That was a good catch.
What by that? So capital A is not.
Yeah, mine's still broken.
Really? Okay, so what is the,
Okay. I think I found it.
you got it?
Yeah, that was mine. Yeah, it was my mistake. And the last, yeah, I had an error in the last
Who else's is breaking?
one. So here's broken.
Yours is good?
Mine says
Oh, no.
the test
If you go up.
takes 0 position argument, but 1 is
Yeah, I don't know.
Did you pass self?
Oh, man.
All of the methods have to have self.
even the test create.
Even test create, yeah.
Right.
Passed?
It shows a untitled.
Ah,
Yeah, I didn't know that was the name of the special method.
well, it's only because of this. It's only the underscores that tells Python that it's a special method.
Right, but yeah, I didn't know that when you do the plus equals, because yeah, that's a general thing in Python. When you do certain operations like indexing a dictionary, you do like dict name square brackets key. It's actually under the hood, just going dict dot underscore underscore get item underscore underscore.
Yeah,
That's a special method. I don't know the map.
neither did I. God, that's neat. Cool. Is everybody's, no? One more.
Maybe you don't need the letters. Just-
I didn't pass that in one.
That's true. Yeah, you don't have to use the special method if you don't want to. You could just create your own function that is add,
Yeah.
right? And then increment the data yourself.
Yeah, without the underscore.
Exactly. And then in that case, we could have called the function whatever we want.
So there occurs to def under I add, the body of it is literally.
Yeah. This is Luke's code. I'm sure he has a reason for doing it this way.
Yeah, to push a PR to make it lowercase, the A.
It is. I copied it wrong.
Oh, okay. He's using our person, so I don't know if it's.
Yeah, especially, yeah. And like, I should have known because this is not Python convention camel case,
Yeah.
right? That's the JavaScript thing.
Looks like an apple.
Yeah.
So why did it work? Like, you didn't provide anything to the test.
What do you mean?
I mean, you defined a class test case, but in the final line, like unit test document, there's nothing that says that we are testing test case class.
That's true. I don't know what unit test main under the hood is actually doing, but I think it's scanning your environment for any instance of the unit test case class and running it. So it just scans your environment for any tests that exist and then executes them. But a lot of what unit test actually does is a bit of a black box to me.
And this assert is instance. So like a function in the test case class, right? In the function in the unit test class.
No, you could use this function outside of unit test. You don't need the unit test module to do assert as instance.
So what kind of function is it?
I don't think, like, the assert functions are part of,
So the assert keyword can be used anywhere. Like,
Yeah.
at the bottom of that code chunk.
but this method is specific to the unit test module.
I think it's a method from test case, if I remember
Okay.
right. But I'm probably wrong. Check that.
But I mean, that would make sense, right? Because it's inheriting from the unit test case class. Is it still breaking?
But yeah, assert as instance is a method of.
Of the test case class?
Yeah.
Cool.
There's a lot of cool ones in there if you print them out with
Oh,
dir function. There's assert count equal, assert false, assert greater. Lots of, if you run that on unit test case, yeah. So lots of cool functionality.
That works.
Does it have an assert all close test case?
All close is part of the NumPy module.
Yeah.
So what we're doing here is we're just using the assert keyword, which is part of Python standard library by default, and then we're using this method from NumPy.
I noticed in the function above you use the assert method from the test class, but in the function below you use an arrow and assert method.
Exactly. So which is pretty cool because you have a lot of flexibility in what kind of assertions you're making.
So you're not restricted. You should just use
No, which is really cool.
Well, I'm noticing a method called assert almost equals, which I'm guessing does the same thing.
I think it does, but I don't know if it takes NumPy arrays,
Oh,
like a 2D array.
That's fair.
Like it might work on like lists, for example, where it'll check each element of the list, or maybe two floating point numbers. But
You're right.
so this is basically confirming that our thing works, right? So our functions are working as expected.
In your case, like you have stack up and tear down.
Yeah.
Oh, sorry.
Yeah, so this basically you have to obviously set up or something else.
Well, so you'll always have setup and you'll always have tear down. That's how the unit test module knows what to create before running the tests. And I think it's important that they're named like this. But of course, we could just test that. Yeah. It breaks because it didn't find any setup.
Elliot was also pointing out that it's better to use np.testing.assert asterisk. I'm guessing it's a family of functions. On the live stream, Elliot says it prints out which elements don't match if it's just a few. If it's just a few, instead of just returning true and false. Which is, I guess, instead of all close, I see.
Instead of all close, what does he suggest we use?
np.testing.assert, and then maybe hit tab at the end of that, because you put an asterisk there.
Testing dot
Assert.
assert. assert.
Oh, and then one of these. So I guess assert all flows would be the one we use here.
Assertion error.
Oh, I guess they aren't as close.
Well, but the tolerances might be different.
We will move the assert.
Oh, of course, if you're using the. Oh, cool.
So then what does it return if it breaks?
Well, let's see.
Oh, wow, it returns stats.
Yeah, so it's returning basically the whole array because every element is different because of how I did that. But yeah, that's really cool.
I'm going to say thanks, Elliot.
Sweet. So for the last 10 minutes or so, I just wanted to zoom out a little bit and think about what else you could do with unit tests. Like with unit tests, we wrote these pretty sort of contrived examples, I think. But they have a lot of value in a lot of different settings. So for example, I'll just go to a previous project of mine, which is here on GitHub, where I have these different classes. So I have a cell class, a population class, and then just some script that's holding a bunch of random functions like input-output functions. And then there's this test directory, which has basically scripts that test each one of those classes independently. And so this is kind of it's kind of a useful structure because you could basically group all of your tests by the class that they're meant to test. And so as you can expect, these get pretty complicated, right? So like the setup function here is quite large because these are really convoluted classes and there's a lot of things to test. But the idea is every single function that's in the cell module has a corresponding test function in this test cell module or in this test cell script. And you could get really fancy with it. So for example, when you run tests, there's a module in Python called coverage, which is really helpful. And basically what it'll do is it'll facilitate identifying the paths in your code that are not tested. So imagine you have functions that have a lot of conditionals. There's a lot of if-else statements or while loops that are exited when certain conditions are met, like all of this type of stuff. So there's a lot of different independent paths through your code. And the ideal unit tests are gonna identify which of those paths are not being tested to make sure that you write test cases for that. And so what I've done is I've outputted the coverage statistics for my project specifically for population and for cell. So in other words, to what extent is the cell module being tested and to what extent is the population module being tested? So the population module, populations.py, has 100% coverage. So there are no conditions in this script that are not being tested by my test code in test population.py. By contrast, that's not true of the cell class. So the cell class has sort of 100, almost 200 different sort of statements that are being made, test statements in the test cell module. But only a subset of those, but there are some paths through this code that are not being tested, right? So if we go down, this else conditional here has no test case that represents it. If we go further down, there's like this if else statement here was never passed as a test case, so it wasn't tested. So as far as I'm concerned, it's not working. Although I have other reason to believe that it is, but none the case. There's no test that is actually telling me that this is working. And then there's this whole chunk of code at the bottom here that similarly has not been tested. So the coverage module is really helpful in combination with the unit test module to identify what is and what isn't being tested in your code. And this is really good when you have really large projects and a lot of different classes or class methods and functions, and correspondingly a lot of different test cases that have to be performed.
So you can call this in your unit test script?
Yeah, so there's this other package which I've listed here, so nose test. So the nose package, which I think comes with Python by default now, but if you don't have it, you could like pip install nose. And it's basically a wrapper around the unit test module, but it extends its functionality in a lot of different ways. So if you run it from the command line from bash, you could do like nose tests, give it a directory that has all of your test scripts in it, and then you could just pass flags like with coverage HTML output. And so it'll not only run all of the tests in that directory, but it'll also give you all of the coverage stats using the coverage module, which is really helpful. If you just want to see maybe which additional tests you need to create to make sure that you have 100% coverage. So the test can also be combined with a continuous integration service like Travis CI. So this is really cool. If you're working collaboratively on a project through GitHub, for example, Travis will prevent you from making any merges into the repository unless all of the tests have passed. So you can't even modify the existing code base until Travis continuous integration sort of gives you the okay. And then you also get, if you want it, a nifty little badge here in your README telling you that your current build is passing. All of your tests have passed. Travis gives you the okay. What's that?
You have to get 100% to pass?
No, so this here specifically is telling you that all of the tests that you have written have passed. But there's a separate badge you could put here that lists the percentage of code coverage you have from those tests. And so you'll often see another badge next to here that's like coverage 100%. So not only is the build passing, but all paths through the code have been tested properly. And then finally, for really complicated classes, like ones that inherit from others or classes that depend on instances of other classes, or maybe ones that depend on external things like HTTP requests, if like it's a URL type of scenario, you could use the mock package, which can basically simulate an instance of the class that the one you're testing is dependent on. And you could simulate return values and behavior of that class so that you could still test code that depends strongly on other code whose behavior you can't necessarily predict. So this is also useful in cases where you have functions or classes that have some level of randomness to them so that you don't always know what the input-output is going to be. You could mock those return values so you could simulate the randomness so that you could still test the code that depends on those random values, for example. And that's part of the mock package, which I think comes by default with Python now as well. So again, this is sort of a very contrived example of how unit tests work, the idea that you write code to test code. But this could be extended in a lot of ways to make sure that your repositories and that your code base are sort of as stable as possible. And you could integrate them with a bunch of different libraries and give you cool stats about your code and coverage and just basically facilitate debugging, collaboration, and sort of code breaking. Yeah.
In this case, like you have this small data set and then like you test it, it's okay. But sometimes in genomics, let's say you have this FASTA file and all these files, pretty big. And so like generally your code will work on the regular FASTA file. So how do you like provide this kind of thing? Like how do you test it like with a FASTA file?
Yeah.
How is it using regular FASTA file?
Yeah, so I mean, if you think about what a FASTA file is, it's just a string of A, T's, C's, and G's.
The FASTA file is just like an example, but there's like multiple other kind of files that are not easy to produce.
Yeah, so I mean, that's sort of an example of when your code depends on some sort of external thing. So you could mock what that might look like so that you could still test your code using the mock module. In a case of a FASTA file, because it is just a string of A's, T's, C's, and G's, you could just create those strings and test your code. If it's something a little more complicated, yeah, it would require a little bit more thought. And it would depend on what it is the function is trying to do. But in a lot of cases, in my experience anyways, the mock module can be used to simulate those kinds of scenarios so that you can still write the code, or you could still test the code functionality, even though you're not passing those external objects to it necessarily. And there's a bit of a learning curve to using the mock module in my experience, but it's definitely worth the effort because it makes testing a little more broad in scope in that it allows you to test a wider range of scenarios that otherwise would be really difficult to do. Any other questions? Cool.
Yeah.
Thanks, y'all.
Thank you, everybody.
What's the alternative of this unit testing R?